Hi, in this video we are going to start chapter 6 of Edwards and Penney, and chapter 6 is about systems of two first-order differential equations, say for functions x of t, y of t. And as we did when we were considering single differential equations, we often write this system in abbreviated form by suppressing the t-dependence of the functions we're considering. So we could rewrite that system as x prime is f of xyt and y prime is g of xyt. So if the tangent field fg only depends on the values of x and y at time t, and not explicitly on t itself in any other way, in other words, the abbreviated form can be written as x prime is f of xy and y prime is g of xy, then we call the first order system autonomous. And that's what chapter 6 is about. Usually we restrict to just two first order differential equations, but that's really just for simplicity. So almost all of the analytic ideas generalize when you have more functions that you're following in time. And there's most interesting applications are for more than two functions, but the advantage of having just two is that we can study the phase plane and understand what's happening with visualization much more easily than when there's more functions to follow. Okay, so remember in chapter 2 we talked about equilibrium solutions and whether they were stable or not. That whole discussion translates almost word for word when you're considering first order systems. So if you have an autonomous system of differential equations, then an equilibrium solution where x of t is x star and y of t is y star means a constant solution. So equilibrium solutions and constant solutions, those are synonyms. And since constant solutions have zero derivatives, if those are solutions, then they have to make the first order system an identity. So the left-hand side will just be zeros. So the right-hand side will have to be zeros. So x star, y star will have to solve the algebraic system of two nonlinear equations, f of xy equals 0 and g of xy equals 0. And we'll often call the values of the constant solutions, or the constant solution x star, y star, equilibrium points, and another synonym that you'll see in the text is critical points. Okay, so now let's talk about stability. And the intuitive definitions are just the same. So an equilibrium solution is stable, means that if, say at time t equals 0, x of 0, y of 0, or x naught, y naught, is close enough to the equilibrium point x star, y star, then x of t, y of t will stay as close as you want for all later time. And since a lot of you are taking or will take or have taken, even in some cases, analysis, let's write down the precise words for this definition. If we want to stay as close as desired, that means that you might desire to stay any distance epsilon close. So for all epsilon greater than 0, we can start close enough so that we'll stay that close. So there exists a delta greater than 0, which is going to tell us how close we should start. So such that if the distance from the initial point x naught, y naught, to the equilibrium solution, the critical point, x star, y star, which is the magnitude of the difference of the two position vectors. If that distance is less than delta, then that implies that for all later times, so x of t, y of t, the distance from it to x star, y star will always be less than that closest desired number, epsilon. Okay, and then unstable is not stable, so that's just the logical contradiction. If you're going to contradict the quantified definition of stability, I won't write it down. You could. So the logical contradiction of stable being true is that it's not true that for all epsilon blah blah blah. So there's some epsilon for which there does not exist a delta blah blah blah. So there's some epsilon so that no matter how small you make delta, even if you start within that distance delta, then for some of those x naught, y naughts, the x of t, y of t is not going to stay within distance epsilon of the equilibrium point. All right. So the ways in which things can be unstable get more interesting than they were when we consider systems, more interesting than they were in chapter 2. And finally, asymptotically stable means that the equilibrium solution is stable, and furthermore, if you start close enough, so that could be within the same delta that you used for stable, or it might have to be closer. If you start close enough, then x of t, y of t actually converges to the equilibrium point. So it's completely analogous to chapter 2. Okay, so in this video we're just going to introduce the kinds of things we'll be studying in the rest of chapter 6. Often we'll be studying two interacting populations. So this is an example of what's called a competing species model, and I'll explain why it's competing in a minute. So maybe x of t is a squirrel population. You know, it might be measured in thousands of squirrels, and y of t is a rabbit population, measured in the same units, and maybe they're competing on some island sanctuary so that the only way their populations change is from births and deaths. So in part A, if we look at this, if either population is missing, and one of the populations can be missing because, so let's assume, for example, y of t is identically 0. So there are no rabbits. Well, then the second equation is true, because y prime will be 0, and there's a y in every term on the right, so the right-hand side will hold. And the first DE will just read x prime equals 14x minus 2x squared, which is logistic. So you know there's a carrying capacity on that island, and all squirrel populations will converge to that equilibrium solution. All right, and analogously, we could consider the case where the x of t's were identically 0. So in any case, these first two terms in each equation are the logistic part. But notice, when we look at the third terms in each equation, they have negative signs. And so we see that the presence, for example, in the first equation of y slows down the population growth of x, because x prime gets smaller. And it's the same in the second differential equation. The fact that the coefficients are -1 for each of those terms is just to make the algebra easy for us in this. But these last terms are the competition terms. It indicates that probably x and y are competing for the same resources or something. So the coefficients of xy are negative. And we can understand why this model is reasonable if we go back to our reasoning in chapter 2 that led to the logistic equation. So let's study x prime of t over x of t, which is the normalized population change rate per population. So animals per year per animal, right? So maybe one squirrel is, the population is increasing by 1 squirrel per year per squirrel. All right, so let's look at x prime of t over x of t. So that's 14 minus 2x minus y. So this is the normalized population change rate. So remember, the easiest model from calculus times is very effective when x and y are small. The population change rate is just proportional to the population, and you get exponential growth. But as the populations increase, there could be competition for resources, for example, or more fighting, or whatever. So this is a competition term for how fast x of t is growing. Which will inhibit the population growth. And, well, if y of t is present competing for the same resources, then this is just a competition term in the normalized population change rate from y of t. Okay, so apparently in this example, y does not inhibit the growth of the population x of t as much as x of t does. Okay, and we could do the same analysis for the population y of t. And as the signs of the x, y terms change, you can get the opposite of competition terms, which is helpful populations. So each population enhances the other one. Or if one sign is positive and one sign is negative, you get the predator, what are called predator-prey models, where the presence of one population, say the prey, helps the other population increase, say the predator, and the thinking is reversed for how the predator affects the prey population. Okay, so let's find all the equilibrium solutions. in other words, the critical points that make the right-hand side of the first order system 0. So we want to solve 14x minus 2x squared minus xy equals 0 at the same time as 16y minus 2y squared minus xy equals 0. All right, so both of these equations, formulas on the left, factor. So let's factor the first one. So that's x times 14 minus 2x minus y equals 0. And the second one factors into y times 16 minus 2y minus x equals 0. And in order to get an equilibrium solution, both of the left-hand sides have to evaluate to 0. So let's just make a little logic diagram to figure out how this could happen. So for the first equation, it could be that x equals 0, or that the other factor, 14 minus 2x minus y equals 0. Okay, now, if x equals 0, the first equation holds, and so we can go to the second equation. And it could be that y equals 0. And in that case, we'll get the equilibrium point 0, 0. There were no rabbits or squirrels on our island, and there never will be. Or it could be that the 16 minus 2y minus x was 0. Okay, but in this case, x is also 0, so the y equals 8, and so we get 0, 8. So this is the case of there are no x's, and the resulting logistic equation has a steady state population of 8 units of the population y. Okay, continuing to the second possibility in the first equation. So if 14 minus 2x minus y is 0, it could be that y equals 0. Well, in that case, we go back to the first equation and we see that x has to be 7. Or it could be that the 16 minus 2y minus x is 0. And in this case, we have a system of two linear algebraic equations and two unknowns. We all know how to solve those, and the solution is xy equals 4, 6. And we can check, for example, in the first equation, 14 minus 8 minus 6 is 0. And in the second equation, 16 minus 12 is 4 minus 4 is 0. So that was the right equilibrium solution. Okay, so here the picture is from p-plane, which we've already been using for this competition model, and we found the 4 equilibrium solutions, 0, 0, there were no rabbits or squirrels, 0, 8, I always forget who's who here, there were no squirrels, they were all rabbits, so these are the squirrels. These are the rabbits. Double check. Yep, okay. So one other possibility was there were never any rabbits and there were 7,000 squirrels. And finally, the really interesting one here is the equilibrium solution where both populations exist. Okay, in the next video, we're going to talk about how to analytically understand stability using the process of linearization, which we've already used when we're studying single equations. That'll be section 6.2. But right now, we can just look at the picture and guess about the stability of these 4 equilibrium points. So 0, 0. Well, if we look at that picture, all the arrows are shooting out away from the origin, and all solutions that start close to the origin do not stay close to the origin. And so this is unstable. And in fact, near the origin, the x and the y are small. So if you look at the system, if you throw away the quadratic term, you get the linearized system. X prime equals 14x, y prime equals 16y, and both x and y grow exponentially as soon as they're positive. Oh, and in fact, the picture looks like an unstable node. The two eigenvalues for this diagonal linear system are 14 and 16. They're both positive. Or an unstable, the words we used were nodal source. Okay. 7, 0 has the classic saddle-like picture nearby 7, 0. So it looks, if we magnified that picture like we've got a diagram, like this, which looks like a little saddle diagram, and in fact that's true. It's not true that if you start close you're guaranteed to stay close. In fact, unless you're exactly on the x-axis, you're eventually going to go away from 7, 0. And 7, 0 looks like a saddle. So it's a saddle point, which is unstable. And the same is true for 0, 8. And 4, 6 looks like all the solutions in the picture actually are all converging there. And if you magnify that picture, it looks like our nodal sink. Which is asymptotically stable. This is kind of a cool picture because 4, 6 is more than stable. If you look at all of these solution trajectories in the first quadrant, where x and y, x naught and y naught are positive, they all look like they're converging to 4, 6. So it looks like x of t, y of t converges as t goes to infinity to 4, 6, as long as we start out with some of each. So x naught is positive and y naught is positive. And in fact, that's true. Now, later on, we'll study some other competition models And it turns out that if the competition terms have coefficients which are too negative, then the opposite situation happens. One of the populations will die out, and one of the equilibrium solutions along the, and depending on the initial populations, it could be either one, and the populations will limit to one of the equilibrium points on the axes. Okay, we are done.